Welcome to the Manufacturing Engineering Media webinar presentation, Trends in Aerospace Components and the 5-Axis Machines Required to Meet Demand, sponsored by Mitsui Seiki USA. Hello, I'm Jim Sawyer, Executive Editor at ME Media. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsor is Mitsui Seiki USA. From its beginnings in 1928, Mitsui Seiki has had the quest for precision as a primary goal. The company currently offers a lineup of machines extending from jig boring machines to 5-axis machining centers. Scott Walker, president of Mitsui Seiki USA and our presenter, will explain the characteristics of 5-axis machines and will discuss the typical components that these machines can produce. He'll also provide real-world results from major aerospace OEMs. For those of you looking to enter the aerospace market, Scott will examine what is required from a technology point of view, as well as how to compete and how to succeed. Scott has worked in nearly every aspect of the machine tool industry in his more than 35 years in the business. He joined Mitsui Seiki in 1991. Prior to that, he held manufacturing management positions at Akuma Corporation and Pratt & Whitney Machine Tools. You will be able to ask questions during the presentation using the Q&A box that will appear at the right of your screen. Time permitting, these will be answered following the presentation. If time runs out before we can get to all the questions, we will make sure the answers are emailed to you. Also, Scott's presentation includes a video clip. As with all video shown over the internet, the quality of the video depends in large part on the viewer's bandwidth and the number of people accessing that bandwidth. If you do experience difficulty during the presentation, please let us know via the Q&A app. Also, if you have questions about any other aspects of our webinars, please email me at jsawyer@sme.org. I will rejoin you after the presentation with a few concluding remarks. But now, here's Scott Walker of Mitsui Seiki USA. Scott?
Thank you, Jim. Hello, everybody. I would like to welcome all of you, and over the next 30 minutes, I'm going to give you a condensed version of what I see as I travel globally throughout the world, supporting both the aerostructures and jet engine business programs as they're starting to develop. So my presentation is really going to outline two areas. One area is going to be aerospace structural components, and the second will be jet engine components. And there's quite a number of manufactured components in those areas. But before we get into the midst of it, let's take a look at what generally is happening in the aerospace industry. Over the next 25 years, the aerospace industry is planning to build 35,000 new aircraft. Is almost $5 trillion worth of aircraft. You have the markets in North America and in Europe that are very strong aero travel markets, commercial travel. You also have emerging markets in China and in India where you have large populations that are moving up into middle class. So the aerospace demand is going to be quite large, and in order to accommodate this demand, the aircraft manufacturers basically want to make airplanes the same way that automobiles are made. In other words, if you look at the automotive industry today, it is a very finely tuned infrastructure of supply chain elements so that they can get all of the components onto the shop floor and assemble a car in a couple of minutes. The aerospace guys want to do the same thing. I don't think you can put a plane together in a couple of minutes, but they definitely want to increase the amount of aircraft. And for those of you that are in the aircraft industry, if you look, for example, at the 737, which is the most popular 160-seat aircraft in the industry, Typically today they make around 36. They're planning on making 57. You look at the 777, you look at the Airbus 320, all of these rates are coming. So what's going to happen in aerospace supply chain is the supply chain is going to be modified so that it is able to deliver components in a box on the shop floor ready for assembly to feed the demand rates that are coming. So if you are a supplier, there's some basic fundamental elements that your business needs to be able to accommodate. Of course, you need to make good quality parts. That's a given in today's industry, regardless of what it is you manufacture. In aerospace, you also need to be able to be rate ready. This means that you need to have capacity at the peak loads, but also you need to be able to have demand management. Let's say we have a global event like the 2008 financial crisis and the market tumbles. Your capability in terms of output is going to tumble, but you need to be able to stay alive to bounce back for the next demand rate when it picks up. So to do this, what's happening is there's a consolidation taking place in the industry right now. There are a lot of companies that are purchasing companies that manufacture components that have secondary process capabilities like shot peen, or are purchasing outside of their core competencies. You have structures guys going into blades and engines and so forth. So this vertical integration is going on, and the first tier supply chain and the second tier supply chain and third tier supply chain are going to be what is supporting the big OEMs, the big Airbuses and Boeings and GEs, Honeywells. Those guys want to move the responsibility of part component manufacturing down the line. So let's take a look at the top tier structure suppliers. Now this is a group of companies that typically are in the hard metals environment. In other words, they're titanium manufacturers primarily, machining titanium components. And if you are one of these companies, you will certainly recognize the other ones because you're probably competing with them. If you are a second or a third tier company, these would be the types of companies that you would want your salespeople to go pursue, because this is the opportunity area where you're going to be able to pick up some of the machining work. So let's take a look at what's happening and why. This is a slide that shows all of the titanium aerostructural components that are in a 787. Now they're at about build 155, 160. I'm not exactly sure what serial number there are, but there's quite a bit of titanium components that are in this aircraft. And as most of you may be aware, the aircraft design has changed. This particular aircraft is a composite skin, plastic titanium skeleton aircraft. The reason that it's built that way is it is lighter, it glides better at 35,000 feet. Basically, commercial aircraft are gliders, and they are much more fuel efficient, and cost of operating per hour is what the airlines want, because these types of aircraft are economical and allow people to buy seats that are less expensive. So in the other area of structural components, of course, are helicopters, unmanned aerospace vehicles. There's a lot of different types of components that are out there. Now, the way the aero industry looks at capital products is basically they break capital products that make components into 4 categories. So you'll notice up in the upper left-hand corner, category 1 are components that are under 0.5 meters. To the right of that is category 2. These are 1 meter machines, and below that is 1 to 2.5, and to the lower left-hand corner is 2 meters. So I'm going to kind of dissect each of these categories and show you what the market requirements are in there. So let's start with category 1, which are small parts. These are the parts that are typically under a half a meter. And if you look out into the global market, there are literally thousands of these machines. In other words, these machine tools have enough spindle capacity to support components from a half meter size and under. So the reality of this size machine in this market for aerostructures is that there's enough spindles to do it, and the replacement market is primarily replacing old machines, much as with your car. If your car has too many miles on it, starts to break down too much, you go out and you buy a new car. It's the same thing with the machine tool. So category 1, there's enough spindles to support. Here's examples of some of those components. For example, up in the upper right-hand corner, that is actually an end fitting that goes on a composite floor beam that goes into the 787. The component to the upper left-hand corner is a component that Boeing R&D engineered to show all of the different types of machining necessary in a titanium component. Category 2. These are medium-sized machines. These are machine tools that are meter-sized. These are 5-axis meter-sized machines. And if you go out into the global market to support the aerospace 787 program, the 737 MAX program, and the Airbus programs, the marketplace currently between now and 5 years from now will need to have an additional 1,200 new spindles to be able to manufacture enough components to support those aircraft programs. What that means is if you're a job shop or a manufacturer and you're going to the IMTS show in a couple of weeks, a good place to look for opportunities to grow your business would be in this size machine, because the demand is definitely growing in this size machine. Now, these machines typically are heavy-duty, robust machines that have high torque and high thrust capabilities, and they're typically designed to take forged components and remove a lot of the material off of those components. So typically you would be looking at, an example would be landing gear components. If you look at landing gear, they're typically made out of 5553 titaniums or very resilient materials. After all, they have to support the plane on takeoff, on landing, so you want to make sure that the assembly stays together. And they're fairly difficult components to manufacture. This next slide is an example of one of the lines that I'm currently working on. This is the Boeing 777 landing gear line. This is going to be located in Springfield, Ohio. This line is designed to manufacture enough components to make 100 landing gear ship sets per year for the next 20 years. So it's a perfect example of a system that is designed to manufacture components that will meet supply demand for building landing gear for the 777. Let's look at another component. This is a 5553 titanium. If you people are familiar with different grades of titanium, 6AL4 is your what I'll call standard in aerospace structural components, but 5553 and 1023 are materials that are about twice as resilient and twice as hard to machine. These particular components are for supporting the engine on the aircraft. They are engine mounts. They have forward and aft engine mounts. So again, another typical size component that fits within that range of 1 meter. Here's another component. This is a rotor sleeve, and one of the gentlemen from Sikorsky is standing next to it. This is sitting on a standalone pallet, but it is a 5-axis component. It kind of gives you an idea of size and scope. Let's move into Category 3. Now, Category 3 are machines that are capable of handling parts from 1 to 2.5 meters. So they're basically 2.5 meter machines. And typically now you're going to have 2 opportunities to investigate depending on the type of part configuration that you're looking. One is in the upper right-hand corner. You see a horizontal spindle. This is actually a tilt spindle. In other words, the workpiece stays stationary and the tilting, articulating spindle generates the 5-axis movements necessary to do 5-axis machining. And below that is a trunnion machine. That's a 2.5 meter trunnion machine that has the same type of capability, but depending on the type of component that you would be running, you'd have to choose between those 2 configurations. So in the trunnion, since that's more in line with the kinds of products that I build, although I do build tilt spindle machines, but not of that size, This is a carriage assembly. Those gentlemen that are on there are the gentlemen that worked with us on the 53K heavy lift for Sikorsky. They're standing on that Trunnion assembly, so it gives you a little bit of scope of size. And this slide shows exactly the pallet that goes in this system. Now this system also is comprised of a group of machines that are in a flexible manufacturing system so that they can run this thing in a 24/7 environment. The part that's basically being put on it, this is a forging of that component. This is about a 7.5 ton forged component. It is actually the rotor hub that supports the long carbon fiber rotor blades that are on that 53K heavy lift. This shows the component in its semi-finished machine state sitting inside of the machine. And again, this is a 2 meter or 6 foot diameter part. And this is the finished component that is shown before it goes to shot peen. Again, if you look at the bores on the end, they're held within a thousandths. Quite a difficult component to make, several hours of machining, but it gives you a good idea of what that 2.5 meter machine environment looks like. The large category, these are typically components that are over 2.5 meters. If you look out in the industry, there are a lot of multi-spindle machines. These machines can handle parts up to 20, 30 foot long if necessary, although there's not that many style of components out there. This particular market, again, there's enough 5-axis gantry or style machines in that market. Again, it's a replacement market. If you look at companies out there in Russia, they've purchased quite a number of them, and there's companies in the U.S. that have purchased quite a number of them, upgrading them. Very typical type machine for the aerospace industry. These type of machines have been around since the 40s. Very good, very productive type machines. And the types of components that they will see, I'm going to show you one example here. The components are side body cords. This is what fastens the wing onto the fuselage of the aircraft, kind of an important component. This shows the forgings of those components. This particular group of forgings are 5553. You can see in the upper right-hand and lower right-hand corner, there's a number there. It says 41 to 1, 25 to 1. What those numbers are what's called fly-to-buy ratios. So in other words, 41 pounds of material comes off to put 1 pound of component into the air. So quite a large amount of machining and quite a large amount of opportunity for stock removal and component manufacturing and billable hours for machining. So if you're looking at the aerostructures component, the opportunities lie between 1 and 2.5 meters for growth markets. So if you're looking for a growth market opportunity in your shop or in your business, that would be the category machine where you will experience the most growth. If you're looking at large gantry style machines, category 4, or if you're looking at smaller machines under a half a meter, you're really looking to enhance your capability to replace equipment that you have so you can be more productive. So those would be the two categories that would look at for opportunities. So now that we've dealt with the aircraft, that glider, let's look at the engine and the powertrain components that go onto these aircraft. Right now in aerospace, there are a group of new aero platforms that are coming online. One is GE LEAP. Another one is Pratt Whitney Gearfan. The Trent 1000 is a third one. And there's other programs that are coming on like Honda Jet and other engine programs that are all going to be using new materials and new propulsion technologies with the intent of building engines to reduce fuel consumptions by 20%. So some of the programs that I mentioned have that capability, and what that's going to produce is replacement of all jet engines on all existing commercial aircraft over the next 10 years. So between now and 2025, just between LEAP and Pratt, you're looking at over 60,000 engines. You throw the Trent 1000 in there, that's another 20,000 engines. And if you look at this slide with the number of components, it's a lot of parts that need to be manufactured and machined. Now, the engine business is a little bit more along the path of integrated supply as compared to aerostructures. So if you look at this group of companies and the first-tier suppliers and the components that they're supplying, you can see that they've lined up pretty good with the engine manufacturers. So again, if you are one of these companies, you probably recognize your competitors in this. If you are not, this would be the area that you would want to go looking for opportunities in the type of work that I'm talking about. So I break this into two categories for engine manufacturing. Category one are cases and gearboxes. These are the structural components that handle the drivetrain mechanisms, that handle the rotational compressor, cold and hot stage engine components. And if you look at this kind of manufacturing components, these are not easy parts to make. They're very accurate parts. They require a specialized kind of machine tool in order to be able to manufacture these kinds of components in a production environment. There's enough of these machines in the market in order to support this. However, this requires a fairly sophisticated capability. These machines are hand-scraped and fit machines. Not every machine tool builder in the world builds machines like this, so you would need to look at specific high-tolerance type machine tool manufacturers, and they are definitely hand-scraped and fit machines. And again, these machines are built in highly controlled environments. This is actually our shop in Japan. This particular plant maintains temperature to plus or minus 0.4 degree overall, and from floor to ceiling we hold it to 0.2 degree. The plant also is designed to have complete vibrational isolation from all of the shop noise, forklifts, overhead cranes, and such. So there's a group of pylons that support these large assembly bays. Typically those pylons go down 120 foot to bedrock. So it's quite an expensive, sophisticated facility to build this type of machine. Again, as I stated, these machines are hand-scraped, and what you're looking for is to maintain 2 seconds of pitch, yaw, roll when you're scraping the machines and fitting the machines. And people that are familiar with this would understand definitely how difficult that is. So here's a typical example of one of our assembly bays. You can see a line of meter machines. You can see the diffusers up in the ceiling area. You can see the slab that it's laying on, and this is the environment where the machine is assembled, built, and qualified. Everything needs to be qualified for aerospace, and then the machine is packed and shipped to location. So gearboxes are gearboxes, and here's a sample of a variety of different typically types of components that are requiring 1 to 2 tenths true position of bores, cross-bore tolerances of a couple of tenths, extremely high tolerance capabilities. The reason the high tolerance is there is you may have an input shaft that's generating 15,000 RPM, an output shaft that's generating 60,000 RPM. It has to operate in all kinds of environments, so tolerance becomes quite important. The second category in aerospace is true 5-axis simultaneous machining. And this is another interesting technology. 5-axis simultaneous machining is advancing quite rapidly in the global market right now, as the requirements to be able to produce these components without anybody touching them. You want to be able to take a part in and out of the machine ready for assembly. It's not easy to do. So let's look at some examples in this area. Jet engine blades. In other words, the fan blades. This is the component that actually propels the plane through the air. This is a GE90 engine, and here's the fan blade. So if you, for example, fly and get on a 777 and you look at the front of it, you'll see these big black fan blades. Well, that's the picture on the left. And there's a leading edge that's made out of titanium and a trailing edge that's painted black, but it's on that fan. And those are for bird strike and debris. And on the right-hand side, you can see that composite blade being machined. They machine the root and the tip, and we build the machines in order to do that kind of work. In the fan business, if you look at the demand, there are at least 100 units necessary to meet demand for fan blades. So the fan blade lengths, this is a fairly large one. This is almost 3.5, 4 foot length. But there's a lot of blades that fall between the the 18 and 24-inch range, and there's a lot of machines. And these are specialized fan blade machines that are going to be necessary in order to meet that demand rate that's coming in. The other area is single blades. There's a lot of new materials that are coming out, and one of the materials that's coming out is called thialuminite. I'm actually working on thialuminite machining, and I'm going to show that at the IMTS show. Thialuminite is a material that's going to be in a lot of the new jet engines. It's light, it takes heat, it is very resilient, and it's very, very difficult to machine because it's kind of like machining a piece of concrete, so it's not very favorable for a good extended tool life, but it's just a problem that needs to be solved. So thialuminite blade machining is a huge market. There is at least another 1,600 units over the next 5 years that will be required in order to accommodate the demand. If you look at, for example, a LEAP engine, there's 128 blades in each engine. If you're going to build 20,000 engines, do the math. It's quite a number of components. So single blade machining is quite important. This is a picture of a single blade machine. This machine will be the machine at IMTS. Again, it's you hold the blade at both ends and you rotate the blade and run a cutter over the top of it to achieve the geometries for leading and trailing edge that you're looking for. This next slide is showing an integral rotor blade. The acronym is IBR. And what that typically starts out as is a 6AL4 turned solid piece of titanium, and that is then put onto a machine, and you literally carve out all of those blades and then move it to assembly. That's the dream. Typically today these are machined, and then there's a little bit of bench work to take tool marks out of it and such, but we're working to solve that and are very close and have solved it on some of the models. It depends on what the blade profiles look like. But typically these are put on small footprint machines. They're vertical trunnion style, horizontal trunnion style machines. This gives you an example of one of the machines that, again, I'm going to have at IMTS that will show this kind of capability. But what you basically have is, if you look at the base of the machine, it's a big block of cast iron. It's strong and stable, so I can articulate that component in the large trunnion assembly. And then on top of it is a very light Ferrari-style, high-speed, high-XL D-cell assembly for your XYZ. And the reason that you want that is, if you look at these three slides, up in the upper left-hand corner, you can see kind of a porous surface finish, and you can see along that leading edge a lot of divots and such. That is not what you want. That is a very poor blade, very poorly made blade, and efficiency, and this is what these engines are all about, is all about the geometry at the leading edge and the trailing edge. The picture in the middle shows the output of the control for tool path, and then the bottom is much more in line with what you would expect to come off of one of these style of machines for a finished blade. Again, what they want to be able to do is put these into systems that have multiple machines, robot load, unload. The part goes in turn, the part comes out machine finished, goes in a box, and is ready for assembly. So there's a big demand for that style of machine in the market. The other is what I'll call blisks, and blisks and IBRs are actually pretty close to being the same in terms of their types of fan blades, turned ring type looking components as you see in this photograph. However, typically these are flank milled, and flank milled requires the cutter to go the complete depth and kind of carve the material out. It's a different kind of a process. But in this size, in this type, there are enough machines to make this. Flank milling, I think, is going away, and point milling is going to become the dominant application, except perhaps in military applications. So there's enough machines in that market, so it's a replacement market area. The other area to look at is impellers. There are tons of impeller requirements in aerospace and propulsion. There's tons of impeller applications also in the new programs for space. So SpaceX and Blue Origin and those types of guys are also looking, because impellers pump oxygen into solid fuel and make the rocket go. However, impeller machining has been around for a while, and there's quite a number of opportunities that are out there in order to machine them. So it's basically a replacement market. So in the 5-axis simultaneous, your opportunities for growth are going to be in single blade and IBR, integral rotor blade machining. And if you're in the impeller business, then there's enough machines, you're kind of in that replacement market. So I have one video clip that I'd like to share with you, and this is a clip of a 2-meter machine making a component that is really a test component. What this test component does is it measures all of the mass and geometry of the machine in one cutting test, and the little artifact on the left that's showing the tolerances is basically holding all tolerances under 6 microns. So if you look at this, if you are considering running or purchasing 5-axis machines, whether they're Trunnion style machines or they're tilt spindle style machines, this would be something that I would strongly recommend that you talk with your builder, ask your builder to run this test. It's simply a 300 millimeter diameter piece of aluminum, taking a very, very light cut. We're basically going around the OD of that taper cone and machining it, and then we take that taper cone off and it will be put on what's called a tally round, and we would measure the bottom, the middle, and the top, check the diameters, and also check the taper. And that component should be able to come in well under 10 microns. If your machine is really tight, if it's a gearbox style machine, if you're doing 5-axis, you would want to have a target under that. You would want to be under 6 microns, because that will directly relate to how accurately you can make the types of components necessary for the gearbox. We are working on trying to make this a standard artifact for the machine tool industry, but the Bureau of Standards is a slow-moving process, and so we are continuing to work on it. But if you would like to know more about that, please make arrangements to contact me or drop me a note, and I will help you with how that can be incorporated into new equipment, and also as a tool to measure the existing equipment that you have to make determinations of how much life is left in that kind of equipment. So with that, I would like to thank everybody for your time and listening to this. And if you have any questions, please feel free to type them in. Jim, back to you.
Thank you, Scott. That was packing an awful lot of really good information into a fairly short period of time. We have received some questions, and it would be nice to get to all of them before our time is up. So let's get to them. If we do run out of time and we can't answer the questions, we have recorded the questions as typed in along with who sent them, and we'll pass those along to Mitsui Seiki, and you can expect a reply via email. So let's look at our list here, and someone writes in, if I'm not in this business, but I'm a medium-sized machine shop, job shop, how do I get into this market sector?
Well, the entry is really going to your first-tier supply and second-tier supply and quoting the job correctly. The problem with existing equipment, if you look at structural components, is that the typical stock removal rates need to be between 6 and 8 cubic inches a minute for roughing, 2 cubic inches a minute for finishing, cost of cutting edge per cubic inch somewhere around 15% or 15 cents per cubic inch. If you are using standard general purpose machinery that can cut aluminums or steels, and you try to cut these harder resilient materials on it, you're going to not be able to participate, because you don't have you're not going to quote it right, and you're not going to be able to understand what's needed. So my recommendation is, again, go to your machine tool supplier and ask the kinds of questions. Say, I want to get into this business. What do you recommend? Have them help you develop quoting scenarios that give you an opportunity to look at capturing some of the work. Capturing the work is the first phase. What's going to happen is, as more work starts to hit the street, the existing guys are going to overflow, and a lot of that quoted work is going to push into the second tier. So you guys need to kind of look and hunt on the lists of companies that I gave you and pound on their doors. They're looking for suppliers now. Do not go to the OEMs. If you're not an OEM sanctioned supplier, they won't even talk to you. So you need to really work with the first and second tier. If you're a small shop, if you're second tier, then it really comes down to capital. How much capital are you willing to invest to capture the business?
And there are certifications that are required for some of this manufacturing, are there not, just to make sure that the parts are coming out and going into planes are flight worthy?
Correct. Typically, the first-tier supply guys are the ones that do the certification. So if you're a supplier to them, they will be the ones that come in, inspect your CMNs, inspect your equipment, and make you fill out, forms that this was made to the right tolerance, that the material specification was correct. But they're responsible as the individuals that's supplying the box to the assembly floor for the certification, not the guys down the food chain.
And looking at this and seeing that some of these areas are for replacement spindles only while others show growth, you do need to have the ability, the knowledge, the expertise to handle the tolerances and the machining of these hard materials. It's not something that someone can go out a machine, set it up in the garage, and start making money, correct?
No, you need to work with your supplier. I mean, it's not unusual, and I've done a lot of conversions and supplemented businesses into this market. Is the builders have application engineers and programmers and cutting tool guys that have been doing this for a long time, have the experience, and it's not just going out and buying a machine tool and bolting it to the floor and putting power to it and pushing a button. It's new technology. It requires a different kind of approach for manufacturing consistent components, and the suppliers that you work with are the ones that really need to help you and walk you through that process. And then typically what happens is as you become more capable and sophisticated, as in most shops, the people in the shop grab a hold of this and actually take it further than we as suppliers do, because they're the ones that are living with the components day in and day out. They know all the little idiosyncrasies of that particular component, and that's what is their competitive advantage in the marketplace.
Okay. How long does it take to make a new machine productive? And after that point, how long does it take to make it profitable? So two very related but separate questions.
Well, let's take a look, for example, at a 1-meter Trunnion machine. That is about a $2 million machine. That's a lot of capital. And typically, a $2 million machine was going to have an expensive shop rate tied to it. And typically, people look at shop rate by hour or by minute, and I'm not going to spew out a shop rate here. If you want those numbers, I can give it to you at the show. But typically, if you have a titanium component that's going into a 1-meter machine, you need to realistically, after the machine is installed, figure anywhere between 3 to 6 months before that machine is producing parts that can start to generate a revenue stream. Again, that is dependent upon the complexity of the part. But please walk through. It's not just the machine. It's the proper cutting tools. It's the proper coolant. It's the proper tool path. It's the proper tool taper interfaces. It's a system. It's not one thing. It's a group of things. And those group of things need to be balanced in a system so that you get the most cost-effective manufacturing approach. Because if you're looking to get an 18 or 20 or 25% gross rate out of a process, you need to hone in on all of the elements of that process to get the best revenue. So you may be making revenue in 6 months, but a year from now, with 6 months experience, you should be able to peel out another 5 to 8% of costs in that process as you become more familiar with the specific component that you're running.
And along those lines, Scott, how important is throughput in aerospace manufacturing? Are the OEMs pounding on the door saying more parts yesterday, or do you have time to learn how to do this?
Right now is the window. The next 2 to 3 years is the window that people are going to have the opportunity to step into this business, and then after that, the people that are in that business will migrate more heavily towards hard metals because that's the margins are going to be higher. And what typically, happens, if you go back 30 years ago, aluminum was with big axial and radial depths of cut, real low RPM. Somebody came along and determined that if you crank up the spindle speed, you can really rip aluminum with high-speed machining. All of the builders started to build high-speed spindles and high XL decel rates. And today, high-speed machining is the norm for aluminum components. If you aren't in high-speed machining, you're not in the aluminum business. The same thing is going to happen in titanium. So the people that got into high-speed machining in the very beginning grew large, big companies. It's going to be the same thing here. People that get into the materials, the hard, resilient materials like the titaniums and 1023s and all the stuff that we have talked about, it's the same thing. The opportunity in that business is the next 5 years. The people then get in it, they're going to buy more machines because they're going to have more demand put on them to produce more parts. So it's an opportunity. That's why this titanium and jet engine business is an opportunity. There's other markets out there also. This is the one I'm most familiar with.
Okay. Here's a question. I believe this is about the certification. Where does AS9100 tie into the different tier suppliers?
Well, AS9100 is typically a first-tier supply chain. And second-tier supply chain, it depends on how you define first, second, third-tier suppliers. I was presenting in India at a university, and I had the same kind of question come up to me. The typical standards that you'll see out there right now are ISO 9000 series. Those are manufacturable series certifications. The one that you're talking about is an aerospace-specific certification. And that certification is across a pretty broad range of disciplines. So it would be typically a first-tier supply, but I know some second-tier supplies that have that also. And sometimes it's really not so much as the manufacturability as it's the assembly, because assembly also is part of the first-tier supply requirement. Not only do they manage supplied components, but they manufacture some of the supply components, and then they assemble them, and then the assembly then goes into the aircraft. That certification is kind of that process.
All right. We have talked about some materials and some new materials, as well as the machines used to shape those materials, and here's one that sort of puts the two together looking forward. Do you anticipate additive manufacturing making any meaningful headway in aerospace manufacturing in the near to mid-future?
Yes, I'm actually working on some additive capabilities in our machines currently. It's a slow process. It's a process that the material, as it's being added, needs to have the same kind of characteristics that a structural component would be. If you look, for example, at those big side body cords, and you look at how much material is removed, and you think, well, why are they cutting all that material away? Well, on a hard forge like that, when you hammer it, the middle of it cools very, very slowly, so the grain structure is very, very nice. It's the kind of grain structure that you want for a skinny, high-resilient component. Additive manufacturing is great for exhaust systems and such. I think, my personal opinion, and maybe others that are in additive may have a different opinion, I think that the real market for additive is repair. Because, if you're looking at an IBR and it's been damaged, and you can cut the blade off and add back on it and repair it and maintain the same material characteristics. But what I've also seen over additive over the years is when I first saw it almost 16 years ago now, it was extremely slow. Now it's just slow, but that doesn't mean 10 or 15 years from now it won't be very competitive in terms of productivity. It's great for modeling and prototyping, but maybe they'll figure out a way to put the material on faster and more consistently.
Right. And GE has announced that it is going to use, or may even now be applying, parts made with additive processes to its jet engines. So the
Yes,
time
that's a
is
novel
coming,
program.
it looks like.
Mm-hmm.
Yeah.
No, without a doubt. Without it, the one thing about the machine tool industry is that it slowly moves forward, but it does move forward consistently.
Mm-hmm. Well, let's see. That leaves us with just one question then. We're doing pretty well. What products mentioned today will be displayed by Mitsui Seiki at IMTS? I guess they want to, well, here's another question that came in after that, so we're not wrapping up. But what you've talked about today, will this be on display at McCormick Place in Chicago next month?
Yes, I'm planning on bringing one of the 777 landing gear machines to the show. It's a big 1.5-meter Trunnion machine. It'll be all the covers off of it, but it'll give you a good opportunity to be able to walk around and take a look at what robustness means in terms of a machine tool. I'm also going to have a blade machine at the show, machining thialuminite, which I'm not sure anybody else will have that, but it's not easy. I don't have everything solved, but it's a good talking point at this point. I have an impeller machine, and I'm also going to have a special ball screw grinding machine. So a lot of my customers are machine tool builders. I supply machines to most of the machine tool builders in the world because I build ball screw grinding machines and linear guideway machines. So I'm bringing a ball screw grinding machine to the show also, not related to this business.
Okay. Well, that pretty much wraps it up. Oh, we did get a couple of questions about the availability of this webinar in PowerPoint form. We'll have to discuss that, but in about 1/2 hour, so about 3:30 today, it will be available in an archived recorded version that can be played back. For those of you in attendance, if you want to watch it again or want to share it with other members of your team, just use the same registration and sign-in process that you did to sign up for today's webinar and your entrance to it. And we'll see about making it available in other forums as well. But on 24, our platform does have this capability to record the webinar, and it will be available in about 1/2 an hour. Well, here's one last question. So are Tier 2 and 3 companies simply making components? Some of them, yes, and
yes. Here's how I kind of classify that. A Tier 3 company is a job shop company. They have spindle capacity. They're capable of generating tool paths. They're capable of importing a CAD IGES file from somebody and looking at it and generating the tool path and purchasing the tooling and building the fixturing and making a part. So if somebody came to a Tier 3 and said, I want 30 of these, Tier 3 would manufacture them and ship them 30 parts to a specific tolerance. A Tier 2 is a little bit more capable. A Tier 2 would be able to have some qualification capabilities. They might be doing a little bit of subassembly instead of just making the component. Maybe they're making 5 or 6 components and they're doing a subassembly. You'll see a lot of structural people will make not only the structural components, but they'll build the tail wing component on an aircraft, something along those lines. A Tier 1 is a complete supply. They supply the components and everything. So, for example, a Tier 1 would be a company that would take the front landing gear of a 777 and put it in the box. And when it gets to the shop floor for assembly up in the Pacific Northwest, you open up the box, and inside of it is the brake drum, the brake rods, the landing gear, the rubber tire, the bolts, the tools, and everything. So that's kind of how I break Tier 1, 2, 3. So as you move up the tiers, the capability increases, and typically the revenue and responsibility increases to the OEM.
Okay, very much like the auto industry then.
Yep, exactly.
Okay. Well, we're out of time almost, and out of questions certainly. As Scott has shown, 5-axis machine tools do offer a precision-driven solution for a precision-driven industry, aerospace manufacturing. And if you'd like to see some of this technology in person, as Scott said, Mitsui Seiki USA will have it on the floor at McCormick Place, September 8th through 13th in Chicago. They will be in the Metal Cutting Pavilion, and that is the North Hall. Is that correct, Scott?
I believe so, yes. Mm-hmm.
Yeah. Manufacturing Engineering Media has a host of ways by which you can also keep abreast of the latest in technology, as well as the aerospace industry. No, I just got word. No, metal cutting is the South Hall. So
okay, I'm not a sales guy, so I really don't know.
Okay, I'm going to have to bring my compass to Chicago then. As I was saying, we do at ME Media focus on the aerospace industry quite intently, and our Aerospace and Defense Manufacturing 2014 yearbook will be published in September. This year's version will include an outlook by Scott Walker himself on the state of the industry, in-depth case studies on machining hard and ultra-hard materials used in aerospace and defense, as well as a look at how additive manufacturing is finding a home in aerospace manufacturing. SME and ME Media also cover aerospace and defense via our monthly Aerospace e-newsletter. And in addition, we invite you to join us at FabTech 2014. That will be November 11th through the 13th in Atlanta, where you can also experience live equipment demonstrations and find cost-saving solutions. We thank you for joining us for this Manufacturing Engineering Media webinar, and we hope you found it informative.